Here we're going to calculate the fugacity of a fluid, in this case HFC 134A, and we want the fugacity 110 degrees centigrade and 4 megapascals. And the way we do the calculation is to use the relation between Gibbs free energy and fugacity, because we can find Gibbs free energy from enthalpies and entropy. So the equation that we're going to use, Gibbs free energy at condition 2 minus Gibbs free energy at condition 1, but at the same temperature, RT log of fugacity 2 over fugacity 1. And we're interested in Gibbs free energy 2 at conditions 110 degrees C and 4 megapascals. Now, Gibbs free energy 1, we're going to pick conditions so that we can do the calculation, namely, has to be at the same temperature. But we're going to pick a low pressure, sufficiently low that we can treat the fluid as an ideal gas. And so I'll show you a chart in a minute where we're getting the data. And on that chart, the lowest pressure is 0.01 megapascals. And so at that condition, the fugacity 1 is going to be the pressure, because we're treating it as an ideal gas. Ideal gas fugacity is the pressure. So then we're going to use the chart to get G1 and G2. So G2 would be H2 minus T S2. So let's look at the chart so we understand how we're getting these values. So first we'll look at generic chart. This is not for the HFC, but it has much less data so that we can more easily understand the behavior. So you'll notice the isotherms, the green solid lines, and at the very low pressures, the isotherms are vertical. The enthalpy does not depend on pressure for an ideal gas, and then they deviate significantly at the higher pressures. And then the dashed lines are the entropies. And so we're going to use this general idea to look at data for HFC 134A. So here's HFC 134A. We see 110 degrees. So we follow this line, and we're looking at where the pressure that intersects that line. So that's where we're trying to determine fugacity. And then if we look at the other end, since we have to do it at the same temperature, here's the ideal gas at the low pressure. So we're going to read values off the chart, and these lines are the entropy lines. So G2 from the chart is going to be 445 kilojoules per kilogram minus temperature, which is 110, but it has to be absolute temperature, and the entropy of 1.72, and this is kilojoules per kilogram per Kelvin. And so that number is minus 214 kilojoules per kilogram. So we can do the same for G1, and I'm going to pause and do that. So now we can calculate G2 minus G1. Do that. 172 kilojoules per kilogram. I'm going to write that as 172 joules per gram. And now this equation has to be in moles that we're using to calculate fugacity. So I'm going to have to multiply by the molecular weight, 102 grams per mole. So now I'm going to substitute into my original equation now that have difference in Gibbs free energy in joules per mole. So the right side are and also joules per mole Kelvin, temperature absolute, and then the log fugacity 2 over fugacity 1, which is 0.01 megapascals, which means our fugacity is going to be in megapascals. And if we solve this equation, we get 2.47 megapascals. So that's the fugacity, 110 degrees, 4 megapascals. And notice the fugacity is less than the pressure too.